Last time when we stopped, I had just begun to derive the differential equation of heat conduction. And I think I told you that the reason why we need a general differential equation is that we would like to solve problems in which the temperature is not just varying in one direction, and also situations in which the temperature is varying with time. So far, we have only considered problems in which temperature is varying in one direction and we have a steady state temperature distribution. If we want to solve more general problems, problems in which temperature varies in more than one direction or problems in which there is a variation with time, then we need to derive a general differential equation for heat conduction to take care of more general situations. Now, for solving the differential equation, consider that we have any arbitrary solid like this, any arbitrary solid. And to derive a differential equation, you always need to take an element inside this solid. Let us say we are going to do the derivation in the Cartesian coordinate system. So, we will take a differential element dx, dy, dz, all right, anywhere, it may be anywhere in this solid, arbitrarily located inside this solid. And here on the right hand side, you have a magnified view of that differential element. Okay, now, we will make some assumptions, and with those assumptions, we will proceed now to derive our differential equation. First of all, the first assumption which we are going to make is that the material is isotropic. The material is isotropic. What do we mean by this assumption? We mean that the thermal conductivity of the material is not directionally dependent. At any point inside the solid, whichever direction the heat may flow, the value of K in all those directions will be the same. You understand? That is what we mean by an isotropic, the assumption that the material is isotropic. Now, K may vary from point to point, but at any given point, it does not matter which direction the heat is flowing, the value of K will be the same. So, we are going to make that assumption. And now, consider again, let us look at the element again, consider this element dx, dy, dz, all right. Now, in this element, let us look at the two x faces, that is faces which have whose normals are in the x direction, that is this direction. There is one face at the back here like that and one in the front here. Let us take, this is our positive direction, all right. So, let us say the heat flowing in the positive direction in this face, it will be dqx, some differential quantity because it is a differential element, and the heat flowing out here will be dqx plus dx because we have moved a distance dx forward in the positive x direction. So, for the two faces which have their normal in the x direction, the heat flowing in, that is the heat flowing in the positive directions, are dqx and dqx plus dx. Similarly, for the y direction, we will have dqy, dqy plus dy, and for the z direction, we will have dqz, that is the bottom face of this element, and going out from the top face dqz plus dz. Now, we will use Fourier's law of heat conduction to write down expressions for each of these quantities. What will we get from Fourier's law? We will get the following. Let us look at the first one, dqx. By Fourier's law of heat conduction, dqx will be equal to minus k dt dx multiplied by, this is the heat flux in the positive x direction, multiplied, we want the rate at which heat flows. So, multiplied by the area of that face, which will be dy dz. all right. So many watts is the rate at which heat flows into this x phase. Now, let me go back for a moment. We were deriving a general differential equation. So, let me add on, make it more, go back and say for a moment, let us also assume, apart from the material being isotropic, let us also assume that heat could be generated in this material, and that the rate of heat generation, assume heat generation assume that heat could be generated in the material, and that the rate of heat generation is Q bar, so many watts per meter cubed. All right. We will use the symbol Q bar for the rate at which heat is being generated per unit volume of the solid. Q bar may be a constant if heat is being generated uniformly. Q bar may also vary from place to place, in which case it will be a function of x, y, z. Q bar could also vary with time, in which case it could be a function of x, y, z and time. Whatever it is, it will be some specified function, or it will be specified to be a constant. So, let us assume there is some heat also being generated. Now, let us go back to where we stopped. Fourier's law tells us the rate at which heat flows in the x direction. So, dqx is this. If I move a distance dx forward in the x direction, then I will get the expression for dqx plus dx, and that will be equal to, I have moved a distance x dx forward in the x direction. Now, we ask ourselves in this earlier expression, what are the quantities that may vary in the x direction? K may vary, all right, because k could be varying from point to point. dt dx may vary, but dy and dz are constants, that is the area of the element that does not change in the x direction. So, k into dt dx may vary in the x direction. So, we will say the following, we will say dqx plus dx. Let me write down the expression first. I will say minus, take it outside, let us put a bracket and say k dt dx. Now, this is the quantity that can vary in the x direction, say plus the variation d dx, the rate at which it varies in the x direction, into k dt dx. All right, into k dt dx multiplied by the distance that I have moved in the x direction, which is dx, all right, and the whole thing multiplied by dy dz, which is a constant, the area. So, this is the expression for dqx plus dx. Any time we derive a differential equation, if I know the value at some distance x, the value at a distance x plus dx will be the increment that occurs, because the function, the quantities that you are concerned with are varying in that direction. All right. Similarly, we can write down expressions for dqy, dqy plus dy, dqz, dqz and dqz plus dz. All right. You can write down expressions for these, and I am not going to do that. I am going to leave it to you to write these down. In the same way that can be written down, these expressions can be written down using Fourier's law of heat conduction. So, now we have expressions for the rate at which heat is being conducted into this element in the positive x direction, the positive y direction, the positive z direction, and the rate at which heat is being conducted out of this element also in the positive x direction, y direction and the z direction. So, we ask ourselves the question, we say all right, what is the rate at which, what is the net rate at which heat is being conducted into the element. So, we say net amount of heat conducted, therefore, net amount of heat conducted into the element into dx dy dz, that is our differential element, into dx dy dz per unit time will be equal to dqx plus dqy plus dqz, this is the flow in, minus the flow out, dqx plus dx plus dqy plus dy plus dqz plus dz. Okay. And when we substitute the expressions we have put down earlier, we will get this is equal to ddx, putting in those expressions and cancelling out, we get ddx k dt dx plus ddy of k dt dy plus d dz of k dt dz, the whole thing multiplied by dx dy dz. This is the net amount of heat being conducted into the element per unit time. All right. Now, the next quantity let us call this as 1. Now, the rate at which heat is being generated per unit time, quantity of heat generated in element per unit time will be equal to Q bar, which is the heat being generated per unit volume, multiplied by the volume of the element dy dx dy dz. Let us call this expression 2. Now, all this is leading up, of course, to applying the first law for a closed system. The third quantity we are interested in is the rate of change of energy of the element. Rate of change of energy of the element. All right. This will be equal to the mass of the element, that is rho dx dy dz, mass of the element, into the specific heat of the material into the rate of change of temperature dt dt. That is the rate of change of energy of the element, and this we will call as 3. Apply the first law for the closed system. What is our closed system? The closed system is the element dx dy dz. Apply the first law of thermodynamics to this closed system. What does the first law say? The first law says 1 plus 2 is the net rate at which heat flows in the element or is generated in the element, must be equal to 3. So, let us do that. Let us substitute now our expressions that we have got, and we will get the differential equation once we do that, and the differential equation we will get would be the following. If I substitute these, I will get the following differential equation for the case that I am deriving. This is the differential equation that I will get. All I have done is put in, this is the term 1, this is corresponding, q bar is corresponding to the term 2, and this is corresponding to the term 3. dx, dy, dz, the volume of the element is cancelled out, it is common to all of them. You follow? So, this is the required differential equation that we were looking for. This is a situation in which we have an isotropic material, we are working in a Cartesian coordinate system, all right. T can be a function of x, y, z and time, that is why we have partial differential equation, and there may be heat generation q bar which may be varying or which may be constant, whatever it is, it will be some specified amount. So, this is the most general form of a differential equation that we have got. All right. Now, let us look at some simplifications of this differential equation. We say to ourselves, suppose the property K, thermal conductivity K of the material is not varying from point to point inside the material. That means, the material is isotropic, K is a constant, the material is what we call as homogeneous, in which case the K can be taken outside the differential here, all right, and we will get the differential equation which is written here. We will get K into d2t dx squared plus d2t dy squared plus d2t dz squared plus q bar is equal to rho Cp dt dt. So, this will be the simpler form of the differential equation that we will get if K is assumed to be a constant. All right, further, suppose, or rather let me for a moment express it in another way symbolically as it is put. Very often the quantity d2t dx squared plus d2t dy squared plus d2t dz squared is written in this form. This is called the Laplacian equation, del squared t plus q bar by k equal to 1 upon alpha dt dt. So, this is another way of writing the same equation, and I would like at this stage to define that we have got here, instead of k by rho Cp, we are writing a quantity alpha here. What is alpha? Alpha is called the thermal diffusivity of the material. It is a combination of three properties: K the thermal conductivity, divided by rho the density, and divided by specific heat, K by rho Cp. All right. So, we define a new property K by rho Cp as alpha, and we put that into the differential equation. So, our differential equation when K is constant can also be written in the form del squared T plus q bar by K is equal to 1 by alpha dt dt. Now, suppose no heat is being generated, there is a case of no heat generation, the q bar term will drop out, in which case I will simply get del squared T is equal to 1 upon alpha dt dt. Suppose in addition there is a steady state, in that case the right hand side will be 0, there will be no change of temperature with time, I will get del squared T equal to 0. You understand? So, this is called Laplace's equation, the last one. So, I have different versions of the differential equation of heat conduction now, and I will use an appropriate differential equation depending upon what problem I am solving, what is the nature of the problem I have to solve. Let us go back again for a moment. If it is the most general form is what we derived first. The material is isotropic, but K may be varying. Temperature may be varying in all directions, and with time there may be heat generation. All right. Next version, K is a constant, in which case I get this simpler version. Third version, there is no heat generation, which case the q bar term drops out. Finally, I say there is a steady state, in which case the dt dt term drops out. All right. So, depending upon the nature of the problem, we will have to use an appropriate differential equation. Now, this differential equation that we have got is for the Cartesian coordinate system. We may sometimes find it convenient to work with the cylindrical coordinate system or a spherical coordinate system. If suppose the object under consideration is a cylinder, in which case a long cylinder or a short cylinder, it will be convenient obviously to work in a cylindrical coordinate system. Or let us say the object is a hollow sphere or a solid sphere, in which case it will be convenient to work with a spherical coordinate system. Now, in the next transparency here, I am showing the two coordinate systems. On the left hand side here, we have the cylindrical coordinate system, all right, shown here, and this is the usual transformation: x equal to r cosine theta, y equal to r sin theta, z equal to z, which helps us to go from Cartesian coordinates to cylindrical coordinates r, theta and z, all right. R is the distance in the radial direction in the xy plane, theta is the angle in the xy plane, and z is the same z as in the Cartesian coordinate system. On the other hand, if I have a spherical coordinate system, I have the transformation x equal to r sin psi cosine phi, y equal to r sin psi sin phi, and z equal to r cosine psi, in which case I have a distance r, which is the distance from the point A to the origin, that is r. Phi is the angle similar to the angle theta in the cylindrical coordinate system, measured in the xy plane, and psi is the angle made by the radius r with the vertical direction z. Psi is called the zenith angle and phi is called the azimuth angle in the spherical coordinate system. I might just write that psi is called the zenith angle and phi is called the azimuth angle. Phi is called the azimuth angle, all right. Now, you might want to remember just these names. So, suppose now I want the differential equation in the cylindrical or in the spherical coordinate system. One way is I can use these transformation formulas for going from Cartesian coordinates to cylindrical coordinates or Cartesian coordinates to spherical coordinates, and by doing transformations just derive it mathematically. The corresponding use whatever is the appropriate differential equation Cartesian coordinates, use these transformations and go to the appropriate equation in cylindrical or spherical coordinates. The other way is to derive again from first principles. We can derive a differential equation using an element in the cylindrical coordinate system or in the spherical coordinate system. Now, let us do that. Let us for instance assume we want to derive a differential equation. Let us say derivation of differential equation of heat conduction in a two-dimensional polar coordinate system. In a two-dimensional polar coordinate system. So, instead of deriving for a cylindrical coordinate system, which is r, theta and z, I am going to derive for a polar coordinate system, which is only r and theta. We will generalize later to r, theta, z, all right. So, let us say we are going to derive a differential equation from first principles, like we did for x, y, z, and we are going to do this derivation for an r theta coordinate system. Assume again material is isotropic and heat generation is Q bar. In so many watts per meter cubed. Q bar may be a function of r and theta, Q bar may be a constant, whatever it is. Let us look. If I want to derive a differential equation in r theta, obviously I need an element in the r theta system. So, let us take such an element now. Let me draw a coordinate system. This is a coordinate system r theta I want to draw. Right. Now, this is the radius r, and this is dr, and this is the angle d theta. So, the element r d the element under consideration is the one that I am shading, and its area will be r d theta into dr. Now, again like last time, let us put down expressions for the heat being conducted in and out of this element. So, we are going to put down expressions for heat being conducted in the r direction into this element, heat being conducted in the r direction out of this element, heat being conducted into the element in the theta direction, and heat being conducted out of this element in the theta plus d theta direction. This is the angle d theta and this is the angle theta. All right. So, we will call these quantities, we will call these as, let me just indicate them. The first one call as dqr, then dqr plus dr, then here I will call this as dq theta, and the last one here I will call as dq theta plus d theta. All right. We want to put down expressions for each of these quantities. What will we get? We will get the following. We put down expressions for these quantities. We will get dqr, the first one. Now, I am not going to explain again like last time, I will simply put down the expressions. dqr will be minus k dt dr multiplied by the area through which heat is flowing. The area through which heat is flowing will be r d theta into 1. We assume in the z direction that we have a unit width. So, that is the area. dqr plus dr will be equal to minus, now we will say here k r dt dr plus ddr k r dt dr into the distance I have moved dr, the whole thing multiplied by d theta. All right. The quantities varying in the r direction are k, dt dr and obviously r. So, all this k dt dr into r has to be taken inside the differential. d dr of all this multiplied by dr is the amount of variation that occurs when we move from r to r plus dr. Similarly, we can write down expressions for dq theta and dq theta plus d theta. For dq theta we will get minus k dt d minus k dt d theta k by r, sorry, dt d theta, because we want a variation gradient of temperature with distance. So, it will be dt by r d theta, the whole thing multiplied by area, which will be dr into 1. And if I move a distance, an angle d theta forward, that is the distance r d theta forward, I will get minus k by r dt d theta plus d by r d theta multiplied by k dt d theta multiplied by r d theta, the whole thing multiplied by dr. Now, therefore, the rate at which heat is being conducted into the element will be dqr plus dq theta minus dqr plus dr minus dq theta plus d theta. And if you do all that, you will get rate at which heat is conducted. In the previous term, you should have an r squared here, r squared d theta, yeah. Rate at which heat is conducted into the element will be equal to ddr into kr dt dr plus 1 upon r dd theta multiplied by k into dt d theta, the whole thing multiplied by dr d theta. That is the rate at which heat is conducted into the element. Okay. Now, this is what we have earlier called as 1. Now, in the same way, the quantity 2, that is rate of heat generation in the element, will be heat generated per unit time, heat generated per unit time will be equal to q bar multiplied by the volume of the element r d theta dr into 1, and this would be the term 2, and finally rate of change of energy of the element rate of change of energy of the element will be equal to the mass of the element rho multiplied by r d theta dr into 1, that is the volume mass of the element, into specific heat into the rate of change of temperature with respect to time, and this will be the term 3. So, 1 plus 2 again by the first law, 1 plus 2 is equal to 3. So, we get the differential equation after and clean up a little, cancel some terms, we will get the differential equation 1 by r ddr multiplied by kr dt dr plus 1 by r squared d d theta multiplied by k dt d theta plus q bar will be equal to rho Cp dt dt. This is our differential equation in the r theta coordinate system, in the polar coordinate system. all right. So, this is how we proceed to derive. Any time you have to derive a differential equation, take an element, apply the first law of thermodynamics, write down expressions from Fourier's law of heat conduction for the rate at which heat is conducted in or out of all the faces of that element. That is really what it comes to, and you will get the appropriate differential equation. Now, once again we can see from this differential equation that if I have a constant k, then I will get a simplified form of this equation for a constant k. If the material is isotropic and the k is constant, for k equal to constant, I will get a simplified form. I will simply get k, I will take it outside the differential. So, k multiplied by 1 by r d dr r dt dr plus 1 by r squared d 2 t d theta squared plus q bar will be equal to rho Cp dt dt. This will be the differential equation that you will get with a constant k. And again, as we did earlier, if it is a steady state problem, then the right hand side will drop out completely, the dt dt term will drop out. If there is no heat generation, the q bar term will drop out, and so on. You can get further simplifications. Now, suppose I wanted to derive this differential equation for an r theta z situation. Suppose I say to you, derive this, we have done for r theta. Now, I say derive the differential equation for the 3-dimensional situation, the 3D cylindrical coordinate system. I ask you to do this. This will be for an r theta z situation, all right. All that is going to happen, if you go through it yourself, is you are simply going to get one more additional term on the left hand side. And what is going to be that additional term? Additional term on left hand side of the equation that we have here will be k d2t dz squared. This is the additional term that you are going to get in this differential equation, all right, out here. That is all that you are going to get, an additional term out here plus this quantity. You got it? This is the term which comes in, because now you have, in the z direction, you have to consider the difference between heat flowing by conduction in the z direction, flowing into the element, and flowing out of the element in the z direction. That is how this extra term is going to come in. So, although we have derived the differential equation for r theta, you can see that extending it to r theta z presents no real problems. Okay. Now, let me just put down the differential equation, show them again for constant k, for let us show the differential equation for r theta z for cylindrical coordinates. This is the differential equation that we have, k into 1 by r d dr d or dr of r dt dr plus 1 by r squared d2t d theta squared plus d2t dz squared, close the bracket, plus q bar is equal to rho Cp dt dt. This is the differential equation you will get for cylindrical coordinates. Okay? And for spherical coordinates, we are not deriving the differential equation, but I am telling you For spherical coordinates, if you do the derivation, you will get this second differential equation on this page. You will get k into 1 by r d2 by dr squared of rt plus 1 by r squared sin psi d of d psi of sin psi dt d psi plus 1 by r squared sin squared psi d2 t d phi squared close the bracket plus q bar is equal to rho Cp dt dt. So, these are the two differential equations you will get for constant k. The first one we have derived, the second one you could derive on your own if you wanted to by taking an element in the spherical coordinate system. That all right? All right, now we move on. So, now we know that given a general situation either in Cartesian coordinates, cylindrical coordinates, spherical coordinates, steady state, unsteady state, variation in one direction, two directions, three directions, isotropic material, constant k, not constant k, whatever it is, you are in a position to put down an appropriate differential equation given a certain solid. Now, in order to solve a differential equation and to get an explicit solution, you need to state certain conditions of the problem. What are those conditions? Those conditions are what we call as initial conditions and boundary conditions. An initial condition is the temperature, an initial condition specifies the temperature at inside the body at some instant of time t equal to 0, from which point onwards we are interested in knowing the temperature distribution in the solid. That is what we mean by an initial condition. All right. So, at t equal to 0, temperature distribution in the body is specified. That is an initial condition. You have to tell your starting point and then say apply the differential equation and tell how temperature will vary with time from that point onwards. That is what we mean by an initial condition. The simplest initial condition is to say, which we use often in solving problems, is that the temperature of the body at the initial instant t equal to 0 is uniform, t equal to T0 or t equal to whatever is specified, T1, some value specified temperature right at the beginning. Now, apart from that, we need to know any solid has boundaries. So, we need to know what is happening at the boundaries of the solid. Those are what we call as boundary conditions. Typically, there are three types of boundary conditions that we specify. Number one, we specify a surface temperature at the surface of the solid. What is the temperature at that surface? This could be some value which could be varying with time or it could be constant. Or we specify the heat flux which is falling on the surface of the body. Or we prescribe the heat transfer coefficient at the surface of the body. These are three types of boundary conditions which we normally deal with: a prescribed surface temperature, a prescribed heat flux incident on the surface, or a prescribed heat transfer coefficient at the surface of the body. Let us now write down expressions for these situations. For example, suppose, let us write down expressions for these. For example, let the surface be a plane face x equal to L. All right. Let us say the surface under consideration is a plane face x equal to L, some surface. Now, at x equal to L, we say at x equal to L, let me draw a surface. This is the solid, and we specify that at x equal to L, some prescribed temperature exists. Let us say temperature is specified with some value T0. So, we will say at x equal to L, the first condition would be, and first type of condition would be T equal to T0. Okay. The second type of condition is of a prescribed flux falling on the surface of the body. So, the second type of condition is, I have got a surface like this and there is a prescribed flux falling on the surface of the body. Let us say that flux is q by a naught, some flux falling on the surface of the body. Let us say it is all being absorbed on the surface of this body. Now, if all the flux that is falling is absorbed on the surface of the body, then by conduction that flux must be flowing by conduction at the surface into the body. So, we equate this flux to the heat flux we will get from Fourier's law of heat conduction at x equal to L, and we can, the second type of condition can be stated as, the prescribed heat flux can be stated as minus k dt dx at x equal to L is equal to minus q by a 0. This is how the second type of condition would be specified. And mind you, I am calling this as the positive x direction. Alright, that is why I put a minus sign on the q by a here. Minus k dt dx x equal to 0, x equal to L is the heat flux by conduction in the positive x direction. This has to be equal to the q by a falling, the q by a is shown falling in the other direction, therefore, it is equal to minus q by a naught. So, this is the second type of boundary condition. This is the first type, T equal to T0, prescribed surface temperature, this is a prescribed heat flux, and the third is a prescribed heat transfer coefficient, in which case I have again a surface like this, alright, and I specify that there is a heat transfer coefficient H at the surface and there is a fluid temperature Tf here. Now, I am going to use Newton's law of cooling and equate it to the heat flowing by conduction in the solid. I have done this earlier when I defined Newton's law of cooling, you will recall. So, the third type of boundary condition would be minus k dt dx at x equal to L. This is from Fourier's law of heat conduction, and this heat conducted must be equal to H, T at x equal to L minus Tf. Newton's law of cooling, heat flux equated to the heat flux by Fourier's law of heat conduction at the interface x equal to L. So, these are typically three types of boundary conditions with which we deal: a prescribed surface temperature, a prescribed heat flux which is equated to the heat flux by conduction from Fourier's law, and a prescribed value of heat transfer coefficient at the surface which is again equated to the heat flux by conduction from Fourier's law at x equal to L. So, this is how we put down conditions. So, the complete formulation of the problem, any problem in heat conduction, means put down an appropriate differential equation, put down appropriate boundary conditions and state an initial condition if it is an unsteady state problem. Otherwise, of course, there would be no initial condition to be specified. You understand? That is the complete specification of a problem in heat conduction. Now, we have come to the end of this topic. Let me introduce you to the next topic which we are going to begin. Now that we have got a general differential equation, we are in a position now to solve problems which are not just one dimensional variations in space, but could be varying with time and with heat generation and so on. So, we are going to next take up some problems of heat generation. We are going to take up some problems of heat generation, and I just wanted to introduce you to the idea that heat generation, where heat generation problems are important in solids. For instance, I may have a nuclear fuel element. Heat is being generated in it because of nuclear fission. I would like to know the temperature distribution in that nuclear fuel element. When concrete sets, heat is evolved when concrete sets. So, I may be interested in the temperature distribution in a concrete slab which is setting, and during the setting process heat is being generated. Or when I have an electrical conductor carrying current, we know that heat is being generated at the rate of I squared R in the conductor. So, that is also a situation with heat generation. I may be interested in knowing what is the temperature distribution in the conductor. You follow? So, there are many situations involving chemical reactions, heat generation due to electrical currents, or concrete hydration, or nuclear fission, where heat is generated inside a solid, and I would like to know what is the temperature distribution in the solid. We are going to look at some problems which are one dimensional and steady state in nature, because here we cannot take up more complicated problems. So, we are going to look at some one dimensional steady state problems with heat generation next.